A very good morning, everyone. Good morning, everyone. Can you hear me?
Good morning, sir. We can hear you, sir.
Oh, perfect. So we just get busy right quick, and we'll try to be very brief with our presentation. So we could take about 2 or 3 of the in-class group presentation. Well, we already have the notes on digital logic online, but just to clarify a few details, we'll look through the digital logic model again, probably in a few minutes, then look up the VHDL implementation of some of the key points. And you should also note that there are some models we may not be able to implement using the VHDL. We may have to implement them on Python, like the Quine-McCluskey and the Espresso and the like. So we may have to implement them on either MATLAB or Python so that the results are implemented on using VHDL code. So we'll see same when we talk about the Karnaugh mapping or Karnaugh map, the Karnaugh maps, either the 2, 3, 4, 5 variables. You realize that in the VHDL implementation, we ended up implementing the results we derived from the minimization, okay? So that the actual algorithm could be implemented either using Python or MATLAB. Okay. Now, before we move on, I'd love you to tell me, what do you understand about digital logic? Let's be a little interactive this morning. So when we say digital logic, what comes to mind? I have a few guys in class. Kaka Ibrahim, can you help us?
It's a way of representing and processing information using ones and zeros.
Okay, using ones and zeros.
Yes, sir.
That's digital logic, right? Perfect. So the bottom line is we want to represent data using ones and zeros. So it's either we go logic gates or we could go Boolean expression. So, well, Boolean as it is the mathematics, okay? Fine. Well, I'll just run through from the logic gate model. So, okay, let's get the right on top. So when we talk about the logic gate model, for instance, here we want to use symbols. And you already know a few symbols we have, but the bottom line is for this symbolic representation, we want to draw a relationship between input and output, okay? And this relationship should be equivalent to some truth table, okay? So in other words, we have the truth table that tells what this logic operation should be performing, and then there's a symbol tied to that, okay? And oftentimes, we want to play with, we want to apply this when dealing with either sequential circuits where we have memory or combinational circuits, okay? Or combinational circuits. Okay, so we'll start off from the combinational circuit perspective, where you already know we have different types of logic gates, where we have the NOT gate. Okay, so what we just have here is so we have XY, for instance. So we feed in an input, and the output is the complement of the input. Okay, so if we feed in a 1, so our output is going to be a 0. If we feed in a 0, then the output is going to be a 1. Then we also have a buffer. Okay, so which is more like a straight through connection. So whatsoever we feed into the input is into the system as the input is what we get as the output. Okay, and we also have other gates, the likes of AND, or exclusive, or we have the NAND gate, we have the NOR gate with their respective truth tables. Okay, so for this we have say AB, then Y being the output. So if we have a 0, 0 for the AND gate, we have a 0. If we have a 0, 1, we also have a 0. So if we have a 1, 0, then we have a 0. If we have a 1, 1, then we have a 1. So we'll see how this works in using the VHDL. Okay. Now the bottom line is Y is the same as A, B. Okay, it's more like a product. Okay, and then we know that the logic gate is something like this. Okay, so we have the OR, which is something like this for 2 inputs. Then the exclusive OR, something like this. Okay, so on and on. So if we should include the NOT gate, then we are going to get our NAND, right? And for our NOR, just all the way. Well, I'm just trying to run through, okay? And another important point I want us to take note of here is that gates generally are grouped into families or logic families. Let's put it that way, okay? And these logic families do obey the static discipline. When we say static discipline, should I feed in an input here, I should get an output. Okay, I should get an output. So that's what it means. So the static discipline just implies that when we, feed the system with some logically valid input, then we should also be able to produce logically valid. Well, if we feed it with logically valid inputs, then we should be able to get logically valid outputs. Okay, and well, I'm going to leave that as an assignment at the end of our slides for you to make a little investigation on the basic logic families. Okay, so you're going to do something on TTL, transistor logic family, the complementary metal oxide semiconductor logic family, the low voltage complementary metal oxide semiconductor logic family, and also the low voltage transistor logic family. So you're going to be taking this as an assignment, and then you figure out, you're going to conduct a little research, okay? So because this brings us into integrated circuits, okay? So integrated circuit. So we're going to see how these designs are made, how we come about the design, how they are principles of operation and implementation strategies, okay? So what do we do with them? At what point do we apply them in our design? So that's what you're going to do. So at the end of the day, before we wrap up the semester, you're going to come up with 1 or 2 ICs, okay, which you will design as part of the hands-on, okay? And then when you when you run through the investigation of these ICs or the logic families, then we're going to talk about the properties, okay? Yeah, and the like. Though we have some, we mentioned them in some of our videos, which I don't want to mention right now, so you can always go back to that. And then beyond this, we also have the transistor equivalent of logic gates, okay? So now you also have that in the notes. I just want to mention it in passing. Now, let's assume we want to implement the NOT gates, okay, X, Y. Okay, so where Y is the same as X inverse. So let's assume we want to implement the NOT gate. So how do we represent this using the transistor as a model? Well, we have, at this point, we just want to play with either the, we want to play with the MOSFET. So we want to look at the N-type MOSFET, metal oxide semiconductor feed effect transistor, or the P-type MOSFET, okay? So when you, well, I wouldn't know if you've taken the course in electronics, but nothing to worry about at this stage, you know, so well, at some point you could also see this as NFET, why this as PFET, whichever way, or you could even see this as NMOS and this as PMOS. But the major point I want you to take note of here is that for the N-type, or better still, NMOS or NFET, it operates more like a switch, okay? The principle of operation is more like a switch. So if we feed in a 0, we get an open circuit, okay? And if we feed in a 1, this is 0. If we feed in a 1, it is a closed circuit, okay? When we feed in a 1, okay? That's the major point. While the PFET is more like an inverted operation. So it is a short circuit when we feed in a 0, and it's an open circuit when we feed in a 1. And we could represent this simply as something like this for NFET, where there are some tests that represents it with a bar before it, so whichever way. Why the PFET, if this is an inverted operation, so it means that we have to have the inversion process. Yeah, so to the gate, so we have this, right? So it could also be represented as something like this, depending on your reference material, okay? Depending on your reference material. So whichever way, okay? Now, the idea is that the NOT gate, the AND gate, the OR gate, NAND, and all of those could be represented through the combination of the N-type and the P-type MOSFET. That's what we're trying to say. So let's assume we want to implement the CMOS inverter. This is more like the CMOS inverter, because this time we are going to be using the transistor equivalent. So here, we already know that the truth table, if we feed in an input of X, then we'll get Y. So if it's a 0, it's going to be a 1 for the output. If it's a 1, it's going to be a 0 for the input. So the point now is, so we want to represent this using these logic. So I have the 2 of them here. So this is connected to ground. So, and this, we have a reference voltage here. Okay, so let's say this reference voltage is 4.0 4.75 volts, right? So say 4.75 volts, for instance. So we have the p-type here, and then we have the n-type here at the gates. And then X being the input. So we're expected to get our Y at the output. So this is a simple combination of the CMOS inverter, okay? And we know that once this is connected to ground, going back to your fundamentals of electrical engineering, we know this is our reference voltage, which is 0 volts, right? Now, if we feed in a 0 as our input, X, so it means, let's change this color. So let's assume X is 0. It's fed to the gate. Now, for the p-type, this is going to act as a short circuit, okay? So if this acts as a short circuit, so it means that this line will be connected to this line. So whatsoever we have as our voltage source is going to appear at this point. Recall your nodal analysis, right? So more like the node voltage. So what we are going to be seeing at this point is 4.75 volts. And now when X is 0, for the n-type, it is an open circuit. So this line is broken, okay? So all that we get is this voltage value seen at the output. So this is going to be high. It's going to give us 1. Is that clear? Kolade Bashar, is that clear?
Yes, sir. Yes, sir. It's clear, sir.
Okay, perfect.
No, sir. Sir, can you please go through it again, sir?
Okay, now,
Thank you, sir.
okay, that's fine. Now, this is the rule of thumb. We are trying to replace gate devices using transistors, okay? And we just presented 2 major models, the p-type and the n-type. And we also mentioned that each gate could be represented by using a combination of these transistors. Now, the n-type operates more like a switch. Once you open up the switch, it is no current flows through. Now, once you trigger the switch, you shut the switch, then we have a short circuit. So that's what it is. So if we, for instance, feed in a 0, for the n-type, we are going to have an open circuit. But if we feed in a 0 for the p-type, there's an inverted operation here. Just assume this is the inversion, okay? Inversion process. But this is the model for the p-type MOSFET, okay? So I want to believe you've done that, your analog electronics, you've done BJT, you've done FET, feed, so you've done all of those, but that is voltage controlled or current controlled devices. Excuse me, and you've also done your CMOS and all of those. Okay, so we are just trying to apply as a switch, okay? Now, if we feed in a 1, for the n-type is going to be a short circuit. Why for the p-type is going to be an open circuit. Now, we just created a model here. Now, let us wipe this. So this is what we have as our circuit, okay? And now, this is the model for the CMOS inverter. So one will confirm if this will give us the same output as we have in our truth table. So for the CMOS inverter, if we feed in an input of 0, then we're going to get an output of 1 because there's an inversion process here. So meaning this is the same as the complement of X. That's the output. So if we feed in a 1, then we're going to get a 0 as our output. Now, let's assume we have the voltage source of 4.75 volts, okay? Theoretically, we want to say 5 volts. Now, it could even be 3.3 if it's a low voltage transistor logic model, okay? Now, it could be, yeah, if it could also be about 3.3 or between 3 to 3.6 volts if we are considering the low voltage CMOS, okay? That's this voltage level. Now, if we are considering the regular CMOS, so we are looking at between 4.5 to about 4.6. So let's assume this now is 4.5 volts. Let's say this is let's say this is 4.5 volts, for instance. Now, what we're trying to say is this: if the input is 0 to this model, so what are we going to get? Let's redraw somewhere else. So let's say X is 0. So we're expected to get our output Y to be 1. So, but looking at the model, the P-type, when we feed it with a 0, it turns to a short circuit. So this is what we're going to get. Our voltage here is 4.5 volts. So this now is going to be replaced with a short circuit, right? And then we have our Y here. Now, when X is 0, now the N-type is going to be replaced with a short circuit. So where we have something coming this way to ground. Okay. Now, this is now what we have. Okay. This is what we have at this point, isn't it? And mind you, this is connected where this is now broken and this is X. Okay. X is 0, but now it has triggered this and we have a short circuit. So it means that current will flow in this direction. And if you recall your nodal analysis, the voltage seen at this node will be seen at this node, isn't it? Is that clear? Is that clear, please?
Yes, sir. Yes, sir.
So it means that this voltage is going to be high because it's going to take on 4.5 volts, which gives us 1. It's not 0, right? So that is what we get here. So which is consistent with this truth table. Now let us assume the input is 1. So this time, let us wipe this. So let's assume that the input is the same as 1. Now, when the input is 1, we have that the P-type is open circuit. It's open circuited rather. So, or it's an open circuit. So it means V is the same as 4.5 volts. And now it is represented with an open circuit. So we have Y, isn't it? So it means that this voltage of 4.5 can only be seen here. V is equal to 4.5 volts. So, but not at this point because it's 0 relative to this point. This is 0 relative to this point. So this is open. It's an open circuit. So current will not flow. But mind you, for the N-type, it is a short circuit. For the N-type, it's a short circuit. So it means this now is going to go all the way. This is a short circuit, but this part is connected to ground with a reference voltage of 0 volts. So it means that, still recall your nodal analysis. So what we are going to see here, it means that no current will literally flow in this direction, but the voltage, the ground voltage will be seen here, which will be 0 volts, which is consistent with this reasoning. Is that clear?
Yes, sir.
Perfect. Now, this is the idea behind representing your logic gates with the transistor model. Now, well, I wouldn't want to go way into others because I would love you to just refer to the lecture notes. We already have, our previous lecture notes. So we have for the AND gate, the NAND gates, the OR gates, the NOR gates, and even the XNOR gate. I know we implemented the XNOR gate in those videos. So the idea follows directly from this principle, okay? So what you just need to do is to figure out a way to, you know, probably represent them by, you know, adopting this logic. And once you do that, no matter how complex or complicated the model may be, you're going to arrive at your final logic model. Okay? Okay. Now, since we have done that, I think we can now move into Boolean algebra. I'll just do a little talk on Boolean algebra, and then we move on, okay? Okay, Boolean algebra. So here we have that Boolean algebra forms the foundation of digital logic design, okay? So we already made mention of the and, or, not, exclusive, or, even the NAND gates, the NOR gates, the exclusive NOR gates, and all of that, you know, and all of these operations could be supported using the VHDL code. We'll play with a few right away. And these operations also allow the representation of any Boolean function, okay? So like I mentioned earlier, when we talk about digital circuits, so when we say digital circuits, two things come to mind. We have the combinational circuit, and then we also have the sequential circuit, okay? Now, for the combinational circuit, we know they are memoryless, more like the NOT gate we just played with. So whatsoever we feed into it is what we get in real time, okay? The present output is a function of the present input, okay? Including your AND gate, and so all of those gates are all of the gates fall under this combinational circuit model, okay? And now for the sequential circuits, where we say they have memory. They have memory because the output does not only depend on the current input, but on some other past values or previous values, okay? So, and an example of this is your flip-flop, right? So it could hold on, it could latch onto a particular value and then process the next value, okay? And there are a few details when we want to consider combinational circuits, okay, in terms of their connection. So we already mentioned also in the previous notes, we have that every of the circuit element is a self-combinational. So every node of the circuit is either designated as an input to the circuit or connected to exactly one output terminal. They also have that the circuits contain no cyclic parts. So meaning every part through the circuit visits each circuit node just once. And then with that, we can now play with the mathematics of these logic circuits, which is the Boolean expression, which deals with those variables. And you already mentioned, you know, as your contribution just before we started talking, that here we are playing with zeros and ones. So it's either a true statement or false statement, okay? And moving on, we'll just make mention of a few details, which we have been using, okay? So the first of which is the complement, right? We have complement. Okay. Now, as at the time I said X is the same as Y, such that Y is the complement of X. So the complement of a variable is just its inverse, okay? So the complement of A is A inverse. That's what it means. Then we also have literal. These are some of the terms we are going to be using over and over and over and over again. So this is just a variable or its complement, just a variable. So A is a literal. Now A bar is a literal. So we can say A is a literal, A bar is a literal. So B is a literal, B bar is a literal, C is a literal, then C bar is a literal. So when we just consider these variables and their complement, you know, as standalone, they are called literals, okay? Then we have what we call product or implicant. Okay, so when we talk about Quine-McCluskey, we'll be talking about prime implicants, okay? But when we say implicant, what we are trying to say is the and of one or more literals, okay? These are literals, okay? So if we take a product of those literals, say A, B bar, this a product, this is an implicant, okay? So we could say A, B, C, this is an implicant, okay? We can go on and on, okay? So it's either we'll call it a product or we'll call it an implicant. Then we also have mean term. So this mean term should not be confused with the implicant or the product, because this the mean term is a function of the number of variables that makes the input, okay? So in other words, the product involving all the inputs of the function is the mean term. So if we have, say, A, B, C as inputs, so the mean term could either be A bar, B, C, it could be A, B, C, it could be A, B, C bar, and on and on. So you note that A, B bar is not a mean term in this case, for which we have A, B, C as the input. So what you should take note of is that the mean term must include all the input functions in the product to be mean term. Okay, so if we have two inputs, then the mean term must be a combination of the two inputs, the product of the two inputs. So that's a clear distinction between the product or the implicant and the mean term. Then another point is the sum, okay, which is more like the or of one or more literals, okay? We say A plus B, okay, or A bar plus C, you know, or whatsoever. And now the max term, just like the mean term, is a function of the number of the number of inputs we have in this expression. And then it must be the sum of all of those inputs. So the sum must include all the inputs of the function. So if we have 3 inputs, then the max term will be the same as A plus B plus C, A bar plus B plus C bar, all the way. Is this clear, please?
Yes, sir.
Yes, sir.
Okay. Now, if that is clear, you also recall that we have what we call BODMAS when you play with algebra, okay? So this just tells us how to go when we have all of these in an expression. So which should we do first? Which should we give, which should we place on a high priority list or whatsoever when analyzing the expression? We have same also, but in logic analysis, we start with the not, then we do and, then before we do or, okay? Not and or, okay? So that's what we do, okay? Which is more like nah, right? Nah. So you have BODMAS here, so we have nah. So we perform not, then we perform and, then we perform or, okay? So say, for instance, so we have A, B plus B, C, D. Let's say B, C bar D. So for us to do this, so, okay, let's place a bar here, B bar. So it means that we have to perform the operation on B bar first. Then before we perform the product, then we have the addition. Then we have to perform the operation on C bar first before the AND operation. Okay, so it goes in that order, okay? And well, in your previous notes, which you have online, we also mentioned the programmable logic array. So I think what we mentioned there is that the Boolean equations could be drawn using, that's a systematic approach, referred to as the programmable logic array. And what this actually says is that, let's assume we have NOT gates. So we could arrange them this way. So where we have A, B, all the way to whatsoever, probably to D or whatsoever. And then we could have our AND gates arranged this way such that we could easily link them up. Let's assume we could easily link them up. So let's assume this is also coming from here. Then let's say this is coming from here. Something like this. All the way. And then we could have our OR gate here, such that all of these point out, you know. So let's wipe this, and this is somewhere below. Let's assume, so all of these so are pointing out, then, so let's assume we have our OR gate here. Then we could link all of this to this to this. Now, this kind of arrangement is what we call the programmable logic array. Okay, so the column for the inputs are drawn, all of these lines for the input, they are drawn. Now the inverters are included in the adjacent columns like we have here. Then the rows of AND gates for each midterm are drawn, all of these AND gates. Then the OR gate is connected to the midterms, you know, in the manner provided. So that's more like the flow, okay? That's more like the flow. Okay, so what else do I want to mention before we begin our presentation? Yeah. Okay. Okay, axioms and theorems. Okay, let's mention that. Axioms and theorems. Let's wipe this. So still on Boolean algebra. So we have axioms. Then we have theorems. So we already know that axioms are basic facts we just hold true, although they may be unprovable, okay? But we just assume they are correct, okay? While the theorems, we could prove the theorems, okay, by, you know, playing with the axioms. So some of the axioms, let's say A is the same as 0 if A is the same as 1. Well, we can prove this, but we cannot prove it, but we just believe it's so. So if A is 0, then it can be 1. And the axioms also, they actually obey the duality principle. So if this is true, then it means that if A is the same as 1, which is duality, then A cannot be 0. So this is the first axiom. So the second axiom is that the complement of 0 is 1. So if we consider the duality, then the complement of 1 will be 0. Okay? Now, this axiom is the not operation, right? This is not operation. why this is complement, right? Now, the third axiom also states that the product of 0 is the same as 0. Same way, the sum of ones by duality is the same as 1. Okay? So this is OR operation, and this is AND operation. So another axiom is that the product of 1 is the same as 1, while the sum of zeros by duality is the same as 0. So another axiom here is that the product of 1 and 0 is 0, which is AND operation, and by duality, the sum of 1 and 0 is the same as 1. Okay? So these are some of the axioms. Then, for the theorems, we have the identity law, where we have A dot 1 is the same as A, and by duality, A plus 0 is the same as A. Then we have the null element law, such that A dot 0 is the same as 0, and by duality, A plus 1 is the same as A, or is the same as 1. Let's take the higher priority. It's the same as 1. Okay? For anything plus 1, A could be 0, A could be anything. So it's going to give us 1. Okay? And then we have the idempotency law, which says that A dot A is the same as A, and by duality, A plus A is the same as A. Then we also have involution, which is the complement of complement, involution law. So if we take the complement of a complement, then we have that element, A. Then we also have complement law, such that A dot A bar will give us 0, because if A is 1 and A bar is 0, then the product will be 0. And by duality, A plus A bar will give us 1. So if A is 1 and A bar is 0, then we have 1. Then we have the commutativity law, which says that A dot B is the same as B dot A. And by duality, A plus B is the same as B plus A. Then we also have associativity law, which says A dot B, okay, dot, because this is associativity. So that will still be dot. Dot C will be the same as A dot B dot C. And by duality, A plus B plus C is the same as A plus B plus C. Okay? So I'll just wipe this. And then we also have the distributivity law, that A dot B plus C, for instance, will be the same as A dot B plus A dot C. And then by, say duality, because this now will be the same as A dot B plus C, right? That's that. So by duality, if we take this out, so that's what we get. So by duality, A plus B dot A plus C will give us A plus B dot C. Then we have the covering law. Covering is V. So we have covering law. Note that A dot A plus B is equal to A. And by duality, A plus A dot C, okay, let's say B is equal to A. Then we also have the combining law. Combining law such that A dot B plus A dot B bar is the same as A. So even when this is 0 and this knocks off to 0, then 1 plus 0 is still 1. So that's A. And by duality, A plus B dot A plus B bar will still give us A. And one final theorem, which is the consensus law. Consensus law. We have that A dot B plus A bar dot C plus B dot C is going to give us A dot B plus A bar dot C. And by duality, we have A plus B dot A bar plus C dot B plus C will be the same as A plus B dot A bar plus C. Okay. Now, these are some of the basic theorems. And then we can talk about De Morgan theorem to conclude on the theorems. De Morgan theorems. So we have the first such that the complement of the product is the same as the sum of complements. Okay. And the second law states that the sum of the complements is the same as the product of the complements. So with this, we could simplify basic circuits, okay, regardless of how large or whichever way. And let's look at one example which we already looked at before. Okay, let's assume we have a y. Okay, let's write this. So let's assume we have y is the same as a bar dot b plus a bar dot b plus a dot b. So I think here b is a bar is common, right? A bar is common. Let's say this is a bar, b bar, a bar. Okay, fine. So a bar is common, so we could bring that out. A bar, b plus b bar plus a dot b. Now, we already know the complements law. So if we invoke the complements law, we have that a plus a bar is the same as 1. So now y will be the same as a bar dot 1 plus a dot b. Okay. Now, you also recall that the identity law states that a bar dot 1 is the same as A bar. So that Y will now be the same as A bar plus AB. Okay? Now, if you look up the axioms, from the axioms, 1.1 is the same as 1, right? So that A dot B is equally the same as either A or is the same as B, okay? Yeah, because they've got the same weight. So technically, from the fourth axiom, Y will be the same as A bar plus B. Okay? So that's just a simple basic problem. Now, let us look up what we have here. Okay, so here we have the VHDL code representation. Okay, so we have the VHDL representation of the Boolean algebra. So we have the Boolean algebra. We have two inputs. So we have declared the inputs. We have declared the inputs, A, B, then the AND output. We have this, the OR output. So we'll play with this. We'll just look up how it works on model sim. Then the exclusive OR output. Then we have the architecture. So AND output is the same as this. We have declared it. We've declared all of this. Then we end that. Okay. Now the next thing is K-map. Okay, fine. For K-map, we have the 2-variable K-map and 3-variable K-map and 4-variable K-map. So for the K-map minimization, well, I'll just mention a few things here. It's a graphical representation, okay? And say Karnaugh map. It's Karnaugh map. That's K-map, right? Okay. So we have that the K-map is a graphical technique used for representing the truth table. We just saw how we're able to use the Boolean algebra to minimize the given logic expression. Okay, so K-map is another way we could do that. And we use the graphical approach. And the number of boxes here will be equivalent to what we have in the truth table. And you know. So that the rectangular shapes will be divided into the squares. And now the number of squares will be the same as the number of lines we have in the truth table, okay? And you already know that the number of lines we have in the truth table is the same as 2 to the n, okay? Where n is the number of inputs, right? N is the number of inputs. So if we have n to be 2, say 2 inputs, A and B, A, B, and where we have the output. So 2 to the 2 will be 4, right? So we have 0, 0, we have 0, 1, we have 1, 0, 1, 1. Okay, so this is what we have for a 2-variable system, okay? And now we have that the output here will be, this is 0, 0, 0, 1. So this is equivalent to A bar, B bar. Then this is equivalent to A bar, B. Then this is equivalent to A, B bar. And this is equivalent to AB. Okay. So we already mentioned that the number of squares we have in the K-map is equivalent to the number of lines. We have 1, 2, 3, 4 lines here. So we have 4 boxes here, okay? So if this is A and this is A bar, so it means this is 1, this is 0. Okay, let's use a different color for that. And then this is B, B bar. So it means that this is 1, this is 0, this is 1, this is 0, right? So AB, this would be AB, then this would be A bar B, A bar B. Now this would be AB bar, A, B bar, and then this would be A bar, B bar, A bar, B bar. Okay. Now, in some other tests, you may want to represent it to look something like this, where you have AB, and this is 1, 0, and this is 1, 0. Okay. And then you could represent whatever you have. So where this is, say, 0, 1, 2, 3. So 0, 0, 0, 0 is here. So this would be, so let's change the color. So it depends on your reference material. So 0, 0 will be at this point. So we're going to plot, this will be 0 box. Then the 1 box will be 0, 1, 0, 1. So this will be the 1 box. Then 1, 0, this will be the 2 box. And then 1, 1. So this will be 3. Okay, so they are, you know, depending on your reference text, you may see the K-map represented in this format where we have numbers assigned to it, where this is 0, 1, 2, 3, depending on the number of variables. Then it could be this format, it could be this format. So if we have to plot this, then we know we are going to plot it here. Okay. So, well, we have the algorithm presented in our previous notes, so we won't go into that for 2, 3, 4, 5 variables, okay? And I'll just, let's play with one simple example, then while we look up other details. So let's assume we want to play with y being the same as a dot b plus a bar. No, let's do a b bar, okay? Now, if we should use the regular minimization technique, so what are we going to get here? Now, this reduces to a into bracket b plus b bar. So we already know based on the theorems that b plus b bar is the same as 1. So this would be a dot 1. So, then y will be the same as a, right? Okay. Now, if we want to implement this on the K-map, so we have AB, so we are going to plot our 1 here, AB. So we have, let's change this color. What do we use now? Okay, let's use black. So I'm going to plot a 1 here. Then we have the next thing is AB bar. So where's AB bar? That's that here. So it means this is what we have. So we have this and this. So what is common? Now we have A bar, B bar, because this is B and this is B bar. So this is going to short out. So what we have left is A, okay? So Y is the same as A. Now, let us look at one more example. So let's assume we want to play with, okay, let's place it here. Y is the same as A bar B plus A bar B bar plus AB. So A bar B, this is 1. Then A bar B bar This is also 1. Then hope I'm plotting the right thing. This is A bar, B. This is A bar, B bar. No, this is not correct. Let's wipe all of this. So A bar, B, this is 1. A bar, B bar, A bar, B bar, this 1. Then AB, this 1. So we have this, and then we have this grouping. Because we could group in 2s, in 4s, and in 8s, okay? So in grouping this, so we have, in this case, A bar, B bar, A bar, A bar, A bar, A bar is common, so we knock that off. So what we have here is B. While on this, B bar is common, we knock that off, so that is A bar. So in this case, Y is the same as A bar plus B, okay? As the minimized. And if we should use the Boolean expression, we should get this, okay? So let's assume, let's wipe this. So let's confirm if we are going to get the same. So we have Y will be the same. So A bar is common. So that would be A bar into bracket B plus B bar plus AB, all right? Then we know this is the same as 1. So that's A bar into bracket 1 plus AB. So that's A bar plus AB. And then we know that this is either A or B. So technically, the Y will be the same as A bar plus B. And that's the same as what we got using the K-map. So you should be able to play with some examples for the 3 variables and all. But this is what I wanted to pick from this. Now you observe that in this 2 variable K-map implementation using VHDL, we have declared the inputs A, B, and F as the outputs. And you realize that in this case, given this expression, A plus A bar B, the final answer when we minimize is AB. And now that AB is what we implemented, okay, like I mentioned earlier, okay? So we implemented the AB as in the VHDL code. So meaning this operation, the minimization operation using the algorithm could be implemented using Python or MATLAB. And then the final result we just implement in VHDL, okay? So the same applies for the 3 variables. So you see that the final answer was implemented here, okay? And for the 4 variables, we have the same thing. And for the 5 variables, we have the same thing. So the Quine-McCluskey is the same as what we call the tabular method. And the same applies. So implementing this directly in VHDL could be challenging, okay? Because due to the iterative and combinatorial nature. So we want to actually pre-process using Python or MATLAB, and then we implement the results, you know, in VHDL. So, well, we have an example also in our previous video, so we don't repeat same content over and over again. So we'll look that up, and now I want to open up the floor for in-class presentation. Okay, so we are 1 hour gone, and just before we move into the in-class presentation, so this is the assignment. So I want you to pick this up. Just pick this before we begin to share our slides. Any questions, please? Any questions so far?
Sir, hello, sir. Sir, can we get your slide?
Why not? Why not? Yeah, I was supposed to upload the last lecture, but a lot of activities, meetings, and I'll try to upload, both lectures, within the week. Okay?
All right, sir.
Oh, you're welcome. Okay. Now, fine. I want to believe you've already taken this. Have you picked this now? This assignment? Have you been able to pick this assignment?
Yes, sir.
Okay, fine.
Yes, sir.
So we should get this submission alongside your slide presentation for next week. Okay, so you want to submit them at the same time. So I think it's about time for us to begin our in-class presentation. So who can share? Okay, so all participants can share. So I think now we want to have group 3 share their slides. Group 3, please come up with your slide and your in-class presentation. So in group 3, we have Olatunji, Haraoye, Olawale, David, Ochefu, Joseph, Olakunle, Jeremiah, Samuel. Are they in class?
Yes, sir. I'm trying to navigate to the slides.
Okay, please do. Okay, while you are trying to navigate through the slides, let's share the model scene platform. We'll give you another 3-4 minutes to get prepared. So this is what we have. So let us look at this Boolean algebra. So let's see, can we open up the Boolean algebra? Perfect. So let's see how this works. Okay. Now, this is what we displayed. So we have others, the 2 variables, 4 variables, and all of that, 3 variables, 5 variables came up. But well, this is about the basic, the simple Boolean algebra. So we already declared the libraries and then the entities Boolean algebra. So we have 2 inputs. And then we want, once we feed in our input, then we want to display the and, or, not, and exclusive or as our output. And then we already have the expressions, the Boolean expression representing the functions. So let us add this to our wave and let's verify if this is running. So add to wave, then, so let us feed in our first input, say input of 0. Input of 0. So now we simulate, right? Boom. So that's what it is. So we have, this is AND. So this should be 0. This should be 0. But our north is high. Okay, not A. So when this is 0, then not A should be high, the exclusive or. So well, let us check out 0, 1. Good. So when we have 0, 1, so we have that sequence too. So now let us try 1, 0. Pause this to 1. Then let's pause this to 0. So we have that. So what if we have 1, 1? Boom. So that's it. So you can see the output of our exclusive OR. So our not A, so when A is 0, not A is 1, and when A is 1, not A is 0. So you can see that AND operation, OR operation, so everything is in order, okay? So it means the program is running perfectly well. So is group 3 ready now?
Yes, sir.
Okay, please share your screen, please. You can begin with your presentation, please.
Okay, sir. Good morning, sir. Can you hear me?
Yeah, we can hear you. You're talking to the class right now. So, and
Okay. Good morning, sir.
just 1 minute before you go on. Every other group should prepare their in-class questions to ask group 3, okay? While I also ask mine. So go ahead, please.
Okay. Good morning, class, everyone. My name is Arai Mohammed Fidaus, as you all know me by my name. This is the beginning of our presentation. Please, next slide. Okay, so in this presentation, we're talking about introduction, Boolean algebras and advanced logic minimization techniques, Boolean functions, Boolean function decomposition and factoring for optimization circuit design, Quine-McCluskey algorithm and Espresso heuristic logic minimization, and introduction to logic synthesis tools and automated digital circuit design. Next slide. So first, we have to understand what Boolean algebra is. So Boolean algebra is a basic math system used to design and simplify digital circuits. So the main goal of Boolean algebra is to simplify digital circuits. So it helps represent and reduce logical expressions. So this makes the system easier to build and understand, because when they are very much easier, you'll be able to understand them better. So logic minimization techniques like the Karnaugh maps, like K-maps, which are widely known, the Quine-McCluskey method are used to simplify circuits by reducing the number of parts needed. So this makes the circuits faster, cheaper, and more energy efficient. So we also have modern tools that use advanced methods to handle large and complex designs. So this helps in creating the small and powerful devices we use today. So I'll be passing over to Tolu.
Okay, good morning, everyone. So today I'll be presenting an essential concept in digital electronics, Boolean algebra, and how it plays a pivotal role in logic minimization, a key process in designing efficient digital system. Now, let's start with the basics. As you all know, Boolean algebra is a branch of mathematics that deals with binary variables, that is true or false, 1 or 2. Now, and it serves as the foundation for digital logic, powering everything from microprocessors to communication devices. Now, there are basic operations. Boolean algebra is built on 3 primary operations, which are the AND, OR, and the NOT. And the AND is a logical conjunction where the output is true if all inputs are true. OR is a logical disjunction where the output is true if any input is true. While the NOT is a negation operation that inverts the input value. Let's look at an example. If A is equal to 1 and B is equal to 0, then A and B equals to 0, while A or B equals to 1 and not A is equal to 0. Now, there are key laws of Boolean algebra. Now, Boolean algebra follows specific laws that help simplify expressions. We have the identity law. For example, A plus 0 is equal to A. We also have the complement law, that is A plus A inverse equals to 1. And we have the distributive law, A times B plus C eloquently. Next slide. Okay, so now we're going to be talking on logic minimization. And why is this important? Logic minimization is the process of simplifying Boolean expression or logic circuits to make them more efficient. Simpler circuits have fewer components, consume less power, and are easier to troubleshoot, making them crucial in modern electronic systems. Now, what are the roles of Boolean algebra in logic minimization? Boolean algebra provides the tool needed to minimize logic by applying its laws. By applying its laws, we can reduce redundancy and create optimized logic design. Okay, for instance, if we were to simplify A times B plus A inverse of B to A, this means fewer gates in a circuit, reducing cost and complexity. Now, to achieve logic minimization, we use techniques such as algebraic simplification, that is applying Boolean law manually to simplify expression. We use Karnaugh maps, which is a visual tool for grouping ones and minimizing logic. We use Quine-McCluskey method. This is a systematic tabular approach to finding the minimal expression. And we have software tools, automated programs that use these tools to optimize circuits. Now, if we were to look at real-world example, if we should consider a circuit with the expression A times B plus A times the inverse of B plus B using Boolean algebra, we can simplify this to A plus B, reducing the numbers of required gates significantly. Now, what are the benefits? What are the benefits of minimization? Logic, that is cost reduction, performance boost, energy efficiency, and reliability. Now, from this, we know that Boolean algebra is not just a theoretical concept, but a practical tool that underpins digital circuit design. And its roles in logic minimization ensures that we can create efficient, reliable, cost-effective systems. That's just basically what it entails. Thank you. I'm going to pass it on to the next person.
Good morning, everyone. My name is Daniel Olawale Daniel. I'm talking about advanced logic in circuit design. So, before I start, let's imagine to design a processor and embedded system on a smartwatch. We know that when we're trying to design something like that, we're going to be small and use as little power as possible. But make sure that every square millimeter counts, and also every milliwatt used, like we save as much as we can. So this is where logic minimization it comes into place, because it's a very important tool in circuit design. So the techniques that we use in logic minimization, first one my list is Boolean algebra. Just like Tolu mentioned, it is a way of minimizing logic. Humans can do that one on paper. So then we use laws like De Morgan's law, distributive or distributive properties. We can also use absorption law, and there are also different laws in Boolean algebra to help us simplify circuits. Another method we also use for logic minimization is Karnaugh map, which also called K maps. It's a graphical, sorry, it's a way of minimizing circuits using tables, where we group ones and then we shorten it. It's a faster way than Boolean algebra. Another way, but Boolean algebra and K-maps are methods that we as humans can easily use for logic minimization. But other ways that an algorithm or a computer can use are Quine-McCluskey method, which also like K-map, but it's a more systematic method of K-map that software tools can use to automate. For example, K-map has a limitation where we can only work up to six segments or six segments, but for Quine-McCluskey method can work more than that. Another technique we also use is Espresso algorithm, which is it's an algorithm that's commonly used for modern CAD tools, CAD tools. Another method we also use is binary decision diagram. It plays a role in minimization for example, in aerospace systems where failures are not an option. Binary decision diagrams helps us to reduce logic, also in a way that there won't be any error. And the final method here is heuristic based. Sorry, okay, no, that's okay. The significance in circuit design. First one, reduce gate count. If I'm trying to reduce a complex algorithm by shrinking it to a very small size, for example, a fingernail, you know that by reducing gate count, by reducing the amount of gates we use, that way we can easily shrink it down to a smaller size. Clean, next slide. Yeah. Another advantage, or why we need logic measurement in circuit design, is super power efficiency. For devices that use battery, like I mentioned at first, a smartwatch, we need to make sure that we use less logic gates so that we won't have to have more switching activities. So using less logic gate by minimizing it is power efficient. The third one is it enhance speed. When you have less logic gates, data flows faster, and then that causes fewer delays. So that's so an optimization for of logic minimization in circuit design. And final one, cost reduction. In a company or in production, in large scale production, when we think of companies producing billions of microchips, we know that if we can reduce as much as can for those that are not needed, not reducing actually, we're optimizing it by minimizing it. But those that has been reduced also helps in saving costs rather than spending extra on those. So then I move on to the next person. Junaid.
Thank you very much, Daniel, and good morning, everyone. So I'm speaking on Boolean function decomposition with a couple of examples. And basically, when you hear the word decomposition would primarily speak of breaking down something, right? So bringing that definition into Boolean function, we say Boolean function decomposition simply refers to the breaking down of complex Boolean functions into simpler subfunctions for easier analysis, optimization, and implementation. Because as earlier stated, many times when we have many of these complex Boolean functions playing out in our digital systems, they take time depending on how complex they are. But when we get to simplify them, break them down into simpler sub-functions, it helps for easier analysis, and at the end of the day, you save more time. Methods of this Boolean function decomposition are your serial decomposition, where functions are split into sequential stages. That is, you are simplifying sections of that functions one at a time. Another method is your parallel decomposition, where your functions are split into different parts and are acted upon immediately. Then you have your iterative composition, where you just you break the complex functions as you keep going on and on and on and on. All right. So and like you said, it's repeated and it's for maximum simplicity. Then you also have those are types where you now have a couple of other methods of Boolean decomposition rather, which is first of all your Ashot decomposition, which divides variables into bound and key to set optimized logic functions which at the end of the day reduces circuit complexity and creates compact design to minimize resource usage in your in your machine or combinational logic. Then you also have your Curtis decomposition, which effectively handles multi-output functions. And what this helps to do is basically to reduce your memory requirements. And like I keep re-emphasizing, at the end of the day, for efficient implementation. Then you also have your Shannon expansion, which splits your function based on variable states. In this case, your true and false, right? Which just aids your circuit synthesis. So it's used more often in testing and debugging to localize errors in digital circuits by basically just isolating those variable conditions. All these are relevant in your logic circuits, in optimization, in your hardware synthesis, to just cater for specific requirements depending on what you are actually trying to achieve at the end of the day. Kunle, please, next slide. So an example of a Boolean decomposition is if you consider the function f of a, b, c, d, which is a simple equation of ab plus cd. A simple decomposition of this would be to put ab as a function of its own, which is h1, then having cd as a function of its own, comprising of c and variable c and d, which is c and d multiplying themselves. Hence, your final or your original function will become f of a, b, c, d to be the addition of the two functions that you've just created. This, in specific sense, is a form of parallel decomposition, which, like I said earlier, takes parts of your complex function and acts upon them. So yes, your Boolean function decomposition finds application in simplifying combinational circuits in digital logic system, optimizing chip areas and power consumption in VLSI design, reducing complexity in state machine, representing compact decision-making process in AI decision trees. So I'll be passing on to the next person, Fidaus, to take over the event. Thank you.
Yeah, cool. Next slide. So I'll be talking about factoring Boolean functions for optimization. So when you factor Boolean functions, so this helps to simplify logical expressions and to reduce circuit complexity, power consumption, and cost in digital systems. So an equation here which says AB plus AC will give you can factor out the common term there, which is A, give you B plus C. So smaller equation will lead to fewer gates, which will lead to faster circuits. So you might ask why Boolean functions, why factor Boolean functions? So this aims to reduce the number of gates needed in a circuit. So it decreases the propagation delay, lowers power consumption, increases speed and efficiency of digital devices. So simple is actually beautiful. The best circuit is not the one with the most gates, but the one that accomplishes the most with the least. Next slide, please. So by applying systematic techniques such as Boolean algebra, Karnaugh maps, or advanced methods like Quine-McCluskey, designers can create efficient and cost-effective circuits. So for Karnaugh maps, it's a graphical method for functions with up to 46 variables. So you group adjacent ones in the K-maps. You group adjacent ones in the K-map to form minimized terms. Also, you can also define K-maps as a graphical approach for minimization based on Boolean theorems and assurances. So like we discussed earlier, we have assurances and theorems that obey the principle of duality. So we have various theorems and we have various theorems of separate variables. So theorems of separate variables are like your commutative law, your distributive law, your associative law, and the likes. But your theorems are like your identity law, your complement law, and the likes too. So here is a diagram for a 2 K-map, and there's also a diagram for a 3 K-map. So for K-maps, we have 2 K-maps, 3 K-maps, 4 K-maps, 5 K-maps. So when you're talking about K-maps, for a two variable, it's 2 raised power n. So for a two variable, that's 2 raised power 2, that's 4. If it's for a three variable K-map, that's 2 raised power 3, that's 6. If for a four variable K-map, 2 raised power 4, that's 16. And if for a five variable K-map, which is actually kind of complex, because when you do a five variable K-map, you are trying to like getting a 3D form in which you have two K-maps, then you join both of them together. So applications of factoring Boolean functions, like what are the benefits? Like where can you apply this? So in microprocessors, they have minimized circuits that improve efficiency in chips, like those used in smartphones, for example, or for control system using robotics and Internet of Things for low power operations. So I'll be passing on to Tunji and Jeremiah to talk more about the Quine-McCluskey.
So yeah, so I'll be talking about the Quine-McCluskey algorithm. So the algorithm is a method to simplify Boolean functions. Is especially useful for automating the process of minimizing logical expressions, as in is an alternative to a visual method like K-maps. So the way it works, the steps, release the min terms. We represent each one in the truth table as a binary min term. Then we group the min terms. We arrange the min terms based on the numbers of one in their binary form. Then we combine them. We merge terms different by one bit, replacing the different bits with a dash. Then we identify the terms that can be reduced further. Those are the prime implicants. Then using a covering table to ensure all min terms are represented in the simplified expression. Now, why we use the Quine algorithm? Unlike K-maps, which become difficult for functions, many variables, the Quine provides a structured, repeatable approach that computers can handle. Pull the next slide ahead. Next slide, So the applications for the Quine-McCluskey algorithm is widely used in digital electronics to design efficient circuits with fewer logic gates, saving cost and power, while it works well for functions with up to 6 to 8 variables. For very complex systems, heuristic methods like Espresso algorithm may be more practical. So is it to optimize digital circuits, computer aided design tools for design system, FPGA and microprocessor logic design. So I'll be passing to the next person. Thank you.
Okay, good day everyone. So continuing on the Quine-McCluskey's algorithm, this algorithm is a very, very efficient algorithm that is used for Boolean logic expressions. It overcomes the efficiency of other Boolean simplification methods such as Boolean algebra or Karnaugh maps. So the Quine-McCluskey algorithm, also known as QMC algorithm, is a very useful algorithm that is primarily used for simplification of Boolean logical expressions, and it is very, very capable of handling more than 4 input variables in Boolean algebra, unlike the earlier mentioned algorithms. So the following are the applications. The first is producing a more efficient method of programming into a computer for digital simplification. So the method of the QMC algorithm, it makes it easier for the computer to program. It makes it easier for the computer to program input variables due to the ability to simplify Boolean logical expressions. So the ability of the QMC algorithm to simplify logical expressions makes it much more easier to represent the behavior of digital logic circuits that are used in our phones, computers, and our other electronic devices. Please, next slide, Kunle. Okay, also the QMC algorithm is also used during the design of digital systems. So typically, digital systems, they require the use of logic gates. And for a more efficient and for a more efficient design of digital systems, because Boolean logical expressions, they can be very complex. They can be a combination of multiple input variables. So the reason why the QMC algorithm is useful is that it helps in breaking down the combination of these input variables to reduce the amount of input elements that are going to be required for the digital systems, which makes it much more efficient, and also it helps to reduce the cost. Also, the QMC algorithm is also capable of producing much more efficient circuits. So I'll be passing on to the next person. Thank you very much.
All right. Good morning. My name is Joseph Izzy, and I'll be dealing with the Espresso heuristic algorithm. So before we begin, I would like to state that the Espresso algorithm is an example of a heuristic program, which basically means a program that proceeds to a solution via trial and error, or by rules that are loosely defined. Heuristic in the sense that there is virtually no existent optimal solution, but rather we proceed to a good enough solution through trial and error. So the Espresso algorithm, therefore, is a resource and performance efficient algorithm aimed at solving the heuristic hazard-free two-level logic minimization problems. Basically, what that means is that the Espresso algorithm solves two-level minimization problems for problems that are often considered as NP complete, which is non-deterministic polynomial time complete, which is the hardest class in the complexity NP class. That is by the way. So basically, when we say a problem is NP complete, that means that there is actually, or rather, there is no deterministic. What's it called? How do I put this? When a problem is NP complete, there is no virtually optimal solution for the problem, but rather the Espresso algorithm helps us to choose or to work out a solution to the problem rather that is good enough. And how this works is we cannot actually verify that the algorithm gives us a solution that actually solves the problem. Rather, we work on an empirical basis, which means that having applied this algorithm to problems in the past and it has provided good enough solutions, we are left with no choice but to believe that applying this problem now to similar problems as to those in the past will also give solutions that are good enough for the required use. So basically, the Espresso minimization algorithm consists of 3 basic steps, which include the first being expand. But before I go into that, I think it's useful to establish the fact that Boolean expressions or Boolean functions can be considered as cubes, where a Boolean function having n inputs is considered to exist in an n-dimensional space with one axis for each of the inputs. So therefore, we can extensively say, or by extension, say that every Boolean function, or every output of a Boolean function with n inputs can occupy n of the 2 n vertices of an n-dimensional cube. So if you have a Boolean function with 2 inputs, that means we have 4 vertices, that's 2 raised to power n, 4 vertices, which signify each of the various states that the outputs can take. Now, the Espresso algorithm works in 3 basic steps. First, we expand, which means we expand the cube until no further expansion is possible without including a vertex of the offset. A vertex of the offset being a point where the output gives 0, or in other words, a mean term of the offset. Now, that means we expand the cube until it is prime. That's another way to put that. So at the end of this expansion process, we have a prime cover of the function such that no prime cube contains any other prime cube. We have covered all ones, in different cubes in the expansion process. Then the next step, we go to the redundant cover, which means we begin to remove cubes that are basically redundant. In other words, we remove cubes such that all the ones remain covered. We do not break the covering property of, of the function, but we only remove redundant cubes which can be removed without destroying the covering property. Then finally, the last step is to reduce. After the expand and redundant cover procedures have been performed, we have a locally optimal solution, which may not be the global optimal solution, because we have to recall that this is an NP-complete problem, where the number of solutions is so large that it is practically impossible to verify by enumeration that we have the optimal solution. So we reduce this procedure then transforms a prime cover into a new cover by replacing each cube with a smaller cube contained within it. Now, after this process is done, we iterate again until it is obvious that there's no further improvement in the optimality of the reduction. So I think it becomes obvious then that the significance of this algorithm will be, for one, for efficient circuit design. If we're able to reduce large cubes to much smaller cubes, then inherently we have less smaller gates needed in hardware, we reduce our power consumption, and of course, that translates to greater speeds and reduced area on chips. And also, that also means we can now deal with larger problems. That speaks to scalability. So now we can deal with larger and more computationally complex set of problems, which would otherwise be prohibited if we were trying to solve with exact methods. So I'll move on to Quine to give us more on the applications.
Okay. Yeah, so Joseph has just told us, sorry. Joseph has just told us about the espresso heuristic method. And so I'll be talking about the applications. So basically it's like you mentioned, it shines when you have a very large number of variables. For instance, you can use a K-map for up to 6 variables. You can even decide to use Quine-McCluskey for 6 variables. But then if you are dealing with something that has maybe 16 variables or 32, or sometimes it grows exponentially large, maybe even up to 50. You will not want to, you won't be able to you can't even use K-maps for those ones. But then using Quine-McCluskey for that will be very difficult. So that's where the Espresso heuristic comes in. Applications that you will usually be dealing with a large number of variables, such as in digital circuit design, you're trying to design a processor. You're obviously going to be dealing with a very large number of variables. You won't always be dealing with just 4 zeros and ones. So it comes in digital circuit design. It also comes in electronic design automation. So things like field programmable gate arrays, programmable logic arrays, and logic synthesis. You want to use Espresso heuristic, even though it doesn't give the what you call a global minimum. Because when I'm talking about like the heuristic thing, there's a local minimum and there's a global minimum. So most times you settle for a local minimum because of the speed that at which it can do that. So to compare with the Quine-McCluskey algorithm, basically I'll say the main thing is the fact that Quine-McCluskey is deterministic and Espresso heuristic is not, in the sense that when you use the Quine-McCluskey algorithm, you are surely going to end up with the best solution, the optimal, the global one. But with Quine-McCluskey, you might not have the best solution. It doesn't guarantee you the best solution, but because of how fast it works, you want to use that for a large number of variables. An example I mentioned here was optimizing a 32 variable logic circuit for a high-speed processor. You can't start doing Quine-McCluskey with that. So that is generally how the both of them compare. It's like a trade-off. You are trading off the precision and the optimum solution for speed, which is a valid trade-off and something that you definitely need to do if you're trying to design very, very high-speed systems. So we'll move on to Victor.
Good morning. Can you hear me?
Yeah, you
Yes.
can.
All right. We'll be talking about logic synthesis tools and automated circuit design. Now, if I got it correctly from Kunle, you see, when applying all these techniques, you find out that in real life applications, we actually work with more complex um, and large amount of kits. For example, when you have maybe like a supercomputer, or you're building a regular computer for that matter, talking about chips and the rest of them, the logic gates that are imbued into these hardware devices are numbered in thousands, hundreds of thousands, and even millions, so to speak. So when you are handling these operations, you see that human ingenuity is not as important, so to speak. So you want to find a way to cut time, make it more efficient, and make things easier for everybody. See, so you can't find humans that would work on millions of logic gates to design millions of logic gates just for one computer. So you know that these things are not efficient when you use human hands on it. So you need to find a way to, bring the effectiveness of an AI or a computer into these processes. So that's what brings about logic synthesis tools and automated circuit design. Now, here it says that it converts high level designs like hardware description languages as for VHDL, which we're treating currently, or Verilog, into gate level netlists. So kind of like series of zeros and ones that the whatever, maybe the FPGA or the ASIC can understand. You understand? So optimize using computers. So for automatic circuit designs, they extend synthesis to physical circuit implementation, tools map optimized designs to hardware like FPGAs and ASICs, include processes like technological mapping and timing application. Now, the focal point here is I want to pass through is this workflow of tools, because this gives you like an insight to how we go from our hardware description languages to down to our hardware building. So we'll get like a very, very hands-on picture of what everything is all about. So starting from HDL design. So we know that we use VHDL or Verilog, whatever the case may be, to create to be able to describe how this hardware you are trying to build is going to function based on the logic circuits involved and whatnot. So in here we have the tools that we use, HDL environments like Vivado, Quartos, Cadence, SymVision, for example. So those are the tools you would work with when you are doing HDL design. Then for RTL analysis, we are talking about register transfer level analysis. So here we are trying to synchronize the timing, the timing correctness of design. So when you are simulating, you need to be able to synchronize the timing of the HDL language you're doing and what you are trying to actualize at the end of the day. So after that, we go to logic optimization. So here, the RTL design here, you are trying to reduce things like power consumption, or try to compress the logic expressions that you have a bit, to make it to use less space, less power and such and such and such. Then you have technology mapping. Here you are trying to map and optimize logical representation of the circuits. Or whatever it is that may be the case. So here you are going to be introducing some hardware components like maybe your flip-flops and the likes of it. So the tools that you could use in this stage would be maybe Synopsys for like ASIC or Vivado for FPGAs. Then we have the gate level netlist of bitstream. So we have gate level netlist for the ASIC, and we have bitstream for the FPGA. So it's more like a recognizable result that you have from all of everything we have done so far that you can now apply as the input to your FPGA or your AIC, as the case may be. So those are basically how the idea works when you're trying to design something from the software and from the software inception down to terminate at the hardware. So, really, next slide, please. So the rest of it is mostly what we've been talking about for all the slides today. So the application of synthesis tools, we use it for CPU and GPU design, for automating processor. I told you that most of these designs have too many complex interconnections of logic gates and the rest, and it will be too bulky for human beings to process on their own. So you need these tools to help you make things easier and the like. So you see ASIC and FPGA coming into light again, and FPGAs are very important when you're trying to perform like diversified operations. ASIC is more more direct and more focused. When you need maybe high performance optimized devices, FPGA will deal with more of versatile applications. You can use FPGAs to do a lot of things, and that's based on the designer's discretion. So advantages of logic synthesis and automation. We know that the automation eliminates manual errors and accelerates design workflows. That much is obvious, because when you automate, you don't have human hands and human errors involved in all of that. So if you have programmed this correctly, then it goes to say that it should work correctly. Then optimization, you achieve minimum gate count. I've explained all of this: reduce power consumption, faster operation. Then scalability simplifies VLSI designs involving millions of gates. So it means that whatever design you come with, you are able to easily scale it into larger or high level applications, larger scale, to involve, maybe you want to create a computer, you can make a language for a small level computer and then to a high level computer like that. Prototyping and build rapid iteration using FPGAs for debugging and testing. So the whole of that is captured inside how trying to make the whole process automated and more efficient.
The speed up.
For
The speed up
yeah.
of the session, we need to wrap up in a minute.
Yeah, I'm already done. I'm done with it. Yeah, that's just the basics of everything.
Okay. Thank you very much for your presentation. So any question, please, from the class?
Yes, sir, I have a question.
Go ahead, please.
Yeah, in their slide, they mentioned defining input and output for the Espresso algorithm, but I didn't, maybe due to like shortness of time or presentation, there was no example. So I would like to know how to specify the input to the Espresso algorithm, and also how to like extract the output after calling the algorithm or something like that.
So over to group 3.
Okay. So the Espresso heuristic algorithm is actually a computer program. It's not something that you do with your hand, actually. It was designed by, I think, there were two major, should I say, developers involved, but it was completed at UC Berkeley. So it's actually a computer program. Um, you can use something like Verilog to do it. So it's just the same. Okay, so if I want to compare it to K-map and Quine-McCluskey, I'll say in a way it is closer to the way we are taught to do K-map, because you take each of the ones, then you group them with the ones around them. That's the expand. Then you're looking at the A redundant. When you just group like that, some of the ones are going to be covered multiple. Like they will have maybe a certain group, a certain one is shown up in two groups. So you're going to now reduce. So that's basically how it works. So in a way, it is kind of similar to K-map, just that it obviously isn't exactly K-map. And So it's just the usual, you have your input and then you have your output. So when you are done with the algorithm, it will give you your answer in sum of product form, basically. Yeah,
All right.
that's
Okay, well, I think the most important thing is that when we talk about Espresso, you want to declare your input in the programmable logic array format, okay? So fine, the computer program takes care of the rest, but that's key when it comes to dealing with that. Well, unfortunately, our time is up and I have some questions to ask. So, but I need to get into another class right now. So hope the class was informative.
Yes, sir.
Okay, so hope to see you in our next class. Bye for now.
Thank you, sir. Bye, sir.